Okay, in this third video in our series on 1D kinematics, we're going to be interested in deriving some equations that are going to help us analyze 1D motion. Okay, so we've already seen these equations here. So we've seen this this equation for the change in time, right? Maybe I won't highlight them all, but we've looked at this one. We've talked about how if we allow t naught to be set to 0, that our delta t ends up just becoming t. We've also defined these following quantities here. So we've also looked at displacement. We've looked at the change in velocity. We've looked at average velocity and average acceleration. So now, let's assume that we're examining some sort of a system in one dimension. We're looking at the motion in that system, where the acceleration is constant. So if the acceleration is constant, our average acceleration then must be equal to our instantaneous acceleration at any point, and this must also be equal to a constant. So this is always the same value. And all these equations that we're going to derive here are only useful if this is true. Okay, so make sure that if we're dealing with a situation where the acceleration changes, we can't apply these formulas blindly. Okay. So let's take a look at generating a few equations that are going to help us analyze this motion. Okay, so in the first case, let's just start off with our expression for average velocity. Okay, so average velocity we've defined as our displacement over a change in time, and we saw that again, this just goes to our displacement over the time if we set t naught to 0. And we've also seen that this is just going to be equal to our final time, which I'm just going to write as x for now, because that's usually when we stop our experiment. So that'll be the x at the end, and x naught, which is our initial position. And really our first equation is just going to come from rearranging these variables here. So if we now slide the t over to the left-hand side, we're going to end up with an equation that looks like this. And then if we just want to isolate the x, we're going to see that we end up with this equation here. And this is our first equation that we're going to find useful in analyzing 1D motion. I'm going to call this one A. And at the end, I'm going to have a summary of all the equations we're going to find useful. The second equation that we're going to find useful really just comes from finding the average velocity again. But if our acceleration is constant, so if A is constant, then it means that the slope of our velocity versus time plot, so imagine we have a velocity versus time plot here, then the slope of our velocity versus time plot must be linear, right? It has to be, basically this plot has to be a line. So imagine we had some velocity versus time plot like this. This would have some slope, and that slope would be equal to our acceleration, and our acceleration would have to be constant because this is linear. So if we had this situation, then we could easily find what the average velocity over any time period was. Let's say we chose some time period in here, and whatever this, let's say this is t naught and this is some t final. At our beginning time here, we're going to have some velocity v0, and we can say at our final time we have some velocity v. Then it must be true, if this is linear, which it must be because we're talking about constant acceleration, then it must be true that our average velocity is just going to be equal to our initial velocity plus our final velocity over 2, right? Because we can imagine if we added the two of these up and divided them in half, we would end up with a value here, and that clearly would have to be our average velocity. Okay, so this is going to be the second equation that we're going to find useful. Maybe let's start the next one. We can probably squeeze it in here. Okay, our third equation is going to come from our expression for average acceleration. So our expression for average acceleration is this right here. And again, we've seen that this will just end up being, instead of over delta t over t, because we're going to let t naught go to 0 again. Now let me write that out in full. So that's going to end up being v minus v naught over t. But it must be true, as we stated above, that if we have constant acceleration, then this means that a bar is equal to a. And so this gives us the following expression. We end up with a is equal to v minus v naught over t, and we can rearrange that in a way that's going to give us, well, I won't skip any steps here. One more rearrangement here, and we end up with an expression in the form that we're going to want to use. That should be a 0. Perfect. And this is our third equation that we're going to find useful. Okay. Okay, so now that we have these three equations, we're going to combine them in a couple of ways to build our fourth and fifth equations, which we're going to find useful in analyzing 1D motion. So let's combine equations A, B, and C in the following way. Okay, so let's start with C. Okay, so equation C tells us that V is equal to V naught plus AT. Let's then add V naught to both sides. Okay, we're allowed to do that. So let's say V naught plus V equals V naught plus V naught plus AT. If we then collect together these two V naughts, we're simply going to end up with 2V naught plus AT. And what we're going to want to do now is we're going to divide both sides by 2. Okay, so if we divide the left-hand side by 2, we're going to end up with V naught plus V over 2 is equal to, dividing this first term, we end up with V naught, and the second term, we're going to end up with a half AT. Okay? If we do that, we can then, well, first we can recognize that from B, equation B tells us that this is just V bar, right? And so let me continue this. Maybe I'll use the right side of the page here. This will then give us the expression in this form here. So we'll have V bar on the left, which is equal to V naught plus a half AT. And A, equation A, tells us that X is equal to X naught plus V bar T, right? So we can rearrange this to give us X minus X naught over T is equal to V bar. And if we substitute this expression into what we had up here, we're going to end up with X minus X naught over T is equal to V naught plus 1/2 AT. And now we're just down to the point where we want to rearrange this. Okay, so we're going to try to isolate just X on the one side. So the way we're going to do that is we're going to multiply through by T. So we're going to end up with X minus X naught equals V0T plus 1/2 AT squared now, because we've multiplied through by T. And then if we slide the X naught to the other side, we're going to end up with X equals X naught plus V0T plus 1/2 AT squared. Okay, and this is going to be our fourth equation. I'll call this one D. And we have one more equation to go. Okay, let me remind myself here. Right, okay, so if we start off with equation C again, and again this tells us that V is equal to V naught plus AT. Rearranging this gives us T is equal to V minus V naught over A. And then B, equation B, gave us that V bar is equal to V naught plus V over 2, right? So if we substitute both of these into equation A, and let's remember what equation A here is. Equation A tells us that x is equal to x naught plus V bar t. So substituting in B and C in here gives us that x is equal to x naught, and so we have our V bar here. So our V bar is going to get replaced with V naught plus V over 2, and our t, which we see up here, is going to get replaced with V minus V naught over A. Okay, so if we do that, we can then pull out this 2 and the A in the basement, and this is going to end up giving us well, first maybe what I'll do, I have to be careful here. I've missed a plus sign. So what I'm going to do here first maybe is let me erase this here, and I'm going to move this x naught over. So we're going to end up with x naught on the left hand side in this way, and then I can rewrite this by just pulling the 2 and the A out of the basement here. We're going to end up with a 2A on the outside, V naught plus V, V minus V naught, right? If we multiply out these brackets, we're going to find that we end up with a V squared minus a V naught squared. And then if I shift this 2A in the basement here over to the other side, we're going to find that we have an equation that looks like this. 2A x minus x naught is equal to V squared minus V naught squared. And then one more rearrangement gives us V squared equals V naught squared plus 2A x minus x naught. Okay, and this here is our fifth equation that we're going to find useful in analyzing 1D motion. So what I've done here is I've collected these equations in a summary here. And so this would be the sort of equations that you would find on a formula sheet. I'm going to put a copy of a formula sheet that I'm going to keep updated up on the website on Blackboard, and you guys would get a copy of this well, for use for assignments or in term tests or a final. Okay, it's not important that you remember how to derive each of these. What's important is that we remember how to use these. And I'm going to be doing, in the next video, I'm going to be doing a bunch of examples where we use these in problems that you guys will find in your assignments, in the term tests, and similar to ones that you're going to find in the final. Okay? So I'll see you in the next one.